So today we will start a new topic and we'll study indirect method of FM generation. We have studied the indirect method of WBFM generation, that is we first generate a narrow band FM signal and then we use the frequency multiplier and we convert it to wide band FM signal. Here I have written WB explicitly like this because we can generate any FM, both a narrow band and wide band signal using indirect method. So that is why, but I have written like this. So we can generate an FN wave by using the modulating signal MT as an external voltage to VCO. Now the question is how to generate a wide band FM signal using indirect method. So for this we use a device that is called VCO, voltage controlled oscillator. This voltage controlled oscillator is a device that generates a cosine or sinusoidal signal with some frequency, and its frequency is controlled by the external voltage or input to this VCO. So if we apply the modulating signal MT as an external voltage to VCO, its frequency will be linearly dependent on the message signal MT. The oscillation frequency of VCO linearly varies with the control voltage. So that is what we want, right? That the instantaneous frequency must change as your message signal changes, or the frequency, more precisely, the frequency deviation must be proportional to MT, right? So if the initial frequency when no input was applied to this VCO was FC, and as we applied this MT as an external voltage to this VCO, its frequency changes as this equation, following this equation. So this is similar, this is the same, I would say, just this proportionality constant must be different. So you can write K here, rather, excuse me. So this is the proportionality constant of VCO or VCO constant. So instantaneous frequency will change as your message signal changes. Next, the question is how to realize this VCO, right? So because we said that VCO is a device which generates a sinusoidal signal of frequency f, and the frequency linearly varies with your message signal MT, or the frequency deviation, right? Frequency deviation by mean when there was no input, the frequency of VCO was FC, or the free running frequency was FC, and when we apply some signal MT, it changes as per this equation. So this fulfills the criteria that a VCO can be used in order to generate a FM wave or FM signal. But the question is how to realize or how to construct the VCO. So this type of devices can be constructed by using resonant circuit of an oscillator. That is, we use L and C, the inductor and the capacitance in parallel, and either we change the value of capacitor as per the input signal MT, or we change the value of inductor as per the input current to some other inductor. So we will focus on this more. So our focus will be on this type of resonant circuit, where we change the capacitance of your input signal, and as we change the capacitance, it will change the instantaneous frequency, because we know that the instantaneous frequency is a function of capacitance. That we'll see more in more detail in later slides. So in order to realize such capacitor, we use a reverse bias semiconductor diode. So a reverse bias semiconductor diode acts as a capacitor whose capacitance varies linearly with bias voltage MT. So if we apply a bias voltage as your message signal, its capacitance will change. How this capacitance will change, we'll see next. This is also known as varactor. So the frequency of oscillation first depend on this, right? we know that all this LC parallel LC circuit, the capacitance, the frequency of oscillation is 1 upon root LC, where C is the capacitor value of the capacitance and L is the value of inductance. So if your C is varied by the modulating signal MT with this equation, so we are using a reverse biased diode. Initially when there was no reverse bias, the value of this, the capacitance of this diode was C naught, and once we apply some massive signal MT, the capacitance of this diode changes as per this equation. So we put value of C here and we see what would be the oscillation, because this C is nothing but this reverse bias diode. So the oscillation frequency omega it would be 1 upon root L C naught minus K MT. That is quite obvious. We have just replaced C with this value. Excuse me, I have some. So the instantaneous frequency in radians per second. So just it's not in hertz, in radians. So omega it is 1 upon root L C naught 1 minus K MT by C naught. Right? We have just I have done. I have just taken this C naught outside from this internal bracket, right? So root L C naught 1 minus K MT by C naught. Next, in order to get step B, what I did, I just took as these two terms separately. We have written just these two terms separately, and I have written this square root of 1 minus K MT C naught by this, which can be also written like this. We can also write this like this, 1 upon 1 minus K MT C naught whole 1 by half can be written like this. It's a simple manipulation. So from step B to step C is a quite trivial step, right? Quite trivial. Next, what I do, we will use binomial expansion 1 plus x to the power n can be approximated by 1 plus nx, if you know, right, under this condition. So we can write this instantaneous oscillation frequency like this, right? We will replace this term by this term if this condition is satisfied, right? So we assume that this condition is satisfied. So we write 1 upon root L C naught 1 plus K MT by 2 C naught. So instantaneous frequency of the oscillator would become this, where K was, if you remember, K was the VCO constant, right? So we can also write this omega it. This C explicitly I am using a approximation sign when we move from step C to step D, right? Because we are using an approximation here. That is why I am using an approximation sign. And when we move from step D to step E, we just do some manipulation. That is why I am writing equal sign. That 1 upon root L C naught is omega C. And if you remember, I told you when no input is provided, the capacitor was this, right? So this is called free running frequency of the oscillator. When no input was provided, the capacitance is 1 upon is C naught. So the free running frequency will be 1 upon root L C naught. So free running frequency of the oscillator ACO is omega C, and the instantaneous frequency can be written like this: omega C 1 plus K MT by 2 C naught, which we can also write like this. I have just taken this omega C inside to this, and we can write instantaneous oscillation frequency like this. So if you remember, the instantaneous frequency of your FM signal is this, where KF is phase sensitivity of the FM modulator, right? So if we just convert it to radians, we can write like this, right? Radian per second, right? So omega C, here omega C is 1 upon root L naught. We compare equation 2 with equation 1. So omega C is 1 upon root L C naught, which I have just written here. And Kf, the frequency sensitivity, is K omega C upon 2 C naught 2 pi, where omega C naught is the free running frequency of your oscillator here. K is the VCO constant, C naught is the initial capacitance, and this is just some constant 2 and 2 pi. So Next we replace k with this. If you remember, yeah. So we can also write k like this, right? So this is the, so we see that this, the output, the frequency is proportional, the frequency deviation is proportional to empty, so it's a valid FM signal, right? So the output of VCO will be a cosine signal with this frequency. So it's a valid FM signal, but how would we match, how would we map our K and with the frequency sensitivity? The K we have to choose like this, right? If our frequency sensitivity is given to us, that we want to generate FM signal with this frequency sensitivity, we have to choose our K in accordance to this equation. So if I ask you, the frequency sensitivity is given to you, C naught and omega C is also given to you. Omega C is nothing but carrier frequency. So free running frequency of your LC circuit, since you are using a VCO, and VCO is this. So how you have to set your value of C naught? C naught you must have to choose some such that it is equal to the carrier frequency, right? So the free running frequency of your oscillator must be equal to the carrier frequency, and you have to choose your ln C naught accordingly. Similarly, if I give you say phase sensitivity, then you have to choose the value of K in accordance with this equation, so that you can generate FM signal of specific parameters. Okay. So next, now we'll see what is the maximum capacitance deviation. Just we'll see how I am, why we are discussing this. So C is C naught minus K empty. So capacitance deviation will be C minus C naught, right? Because this is instantaneous capacitance, and this is the capacitance when there was no empty. So C minus C naught is your capacitance deviation. So max capacitance deviation will be this. So if we write the max capacitance deviation is nothing but K empty max, and if we replace value of K from this equation, we get 2 pi K up to C naught by omega C empty max, and similar we just take C naught here, so delta C by C naught, and if we just write 2 pi 2 K of empty max omega C. This is very trivial step, right? From here to here we have just taken this C naught to the denominator of this, and now we replace omega C by 2 pi Fc, and so this 2 pi will cancel out, and what we have delta C max by C naught as 2 K of empty max. But we have seen this Kf into empty max. This Kf into empty max is nothing but the maximum frequency deviation. If you remember that for any FM signal, the instantaneous frequency is this, and the max frequency deviation is nothing but KFT max, FT max. So max capacitance deviation divided by C naught is nothing but 2 times the max frequency deviation by Fc. So the maximum change in the capacitance would depend on the maximum frequency deviation which we want in our FM signal. That is why we were studying the max capacitance deviation, in order to just show you that it will change, the max deviation in capacitance will change if your maximum frequency deviation of your FM signal changes. So next we will study the demodulation of the FM signal.